researcher at the Albany National Lab, and now he's the assistant professor in the Department of Civil Environmental and Construction Engineering, and also he holds a joint appointment with the Resilient, Intelligent, and Sustainable Energy Systems cluster at the UCL. Okay. So his research mainly centers around modeling and computational strategies for intelligent and resilient critical infrastructure systems with application in transportation and energy. His research was is sponsored by US DOE, UTCs, and other manufacturers and leading energy suppliers. So please join me in welcoming Dr. Wang.
Thank you so much for the introduction. It's really my great honor to be here to share some of my research work. And today's topic is a general stochastic general equilibrium approach for public charging infrastructure planning. And although I kind of framed today's topic under the charging infrastructure, for those of you that are not that into transportation electrification, the general methodology discussed here have the potential to migrate to other systems sharing similar characteristics. So hopefully most of you find this topic interesting. And here's the outline of today's presentation. I will start with introduction, talking about motivation, backgrounds, and challenges. And then I will discuss the methodology and computational techniques I developed to formulate and solve this problem, follow with some numerical examples, and this presentation will conclude with some summarizing remarks and the future research directives. Okay. And during the presentation, if you have any questions, feel free to interrupt. I'll be more than happy to elaborate more. And also, I'll try to leave some time in the end, so hopefully we can have some in-depth discussion. So, as we know, electric vehicles is growing very, very fast. Look at these figures, it's the annual sales in China and in US. As we can see, the exponential trend leads to over 1 million PEV sold in the US, and the number is about 4 million in China. Okay. The PEV here include both plug-in electric vehicles, plug-in hybrid electric vehicles, and battery electric vehicles. Okay. The trend is forecast to continue into the future, into the next 10 years. So this is forecast made by McKinsey. So we can see in China, we are expecting to have over 70 million PEV sold. And this is about 20% of the total passenger cars nowadays. A growing EV adoption naturally leads to a growing charging demand. So in US, we may have the perception that people may be able to charge at home, right? But that may not be the case in other parts of the world. Like for example, in China, as forecast, the majority of the charging demand need to be fulfilled by public chargers, over 80%. Okay, so how we can develop a reliable and robust charging network is very critical for the next 10 years. And here are some maps, and sorry for the resolution. Here are some maps trying to show the current charging infrastructure network in US. And we can see that there are already multiple investors try to join this market, try to provide the charging infrastructure to the public. With this background, the goal of today's presentation is we hope to develop an analytical framework to better understand the interactions between vehicle adoptions, travel behaviors, and also the charging infrastructure investment. Okay. And there are many, many challenges. In this presentation, I will mainly focus on these 4 key challenges. So as I mentioned, there could be multiple decision makers involved in shaping this charging network, right? So we have investors, many, many travelers. Potentially we have governments, utility companies, and also system operators who are kind of making decisions interacting with each other, right? And these decision makers have complicated human behaviors. Like people need to decide where they want to charge, which route to take, for example. And they're making this decision facing enormous uncertainties. Here are some examples like the future EV adoption, energy prices, transportation congestion, and maybe the future policies, right? As a result, because of the first 3 points, the mathematical model to describe the whole system typically be large scale and non-convex. So how can we develop an efficient algorithm to solve this problem is another critical issue. So this is a literature review. Try to summarize some key research related to charging infrastructure. And as we can see, for public charging infrastructure, the majority of the research focus on a central planner perspective. By assuming there is a single decision entities who can optimally decide the layout of the public charging network, right? And depends on different aspects they focus. Some look at power system, try to leverage charging infrastructure to improve the efficiency and reliability of power network. Others look at transportation aspects and addressing the classic facility location problem, right? Either taking a node-based or flow-based approach. And other researchers try to combine transportation and power and propose some unified modeling framework. These are actually all very important work. Essentially, they provide an optimal outcome people can expect when the whole system is under control, right? But we argue with the market growth, with the EV adoption growth, more market participants involved in this market, both supply and demand side, an analytical approach is still lacking to allow us to better understand the system, right? And this is where we hope to make a contribution. So to achieve that goal, we adopt a general MOPAC modeling framework, multi-agent optimization problem with equilibrium constraints. So it's originally proposed by Ferris and Watts in 2012. The idea is actually very straightforward. So consider a system with multiple decision makers, right? Denoted the sets as capital A. And each decision makers have their own decision, denoted as X small a, right? A MOPAC model in its simplest form can be expressed as following. So we want to find the XA in order to optimize certain objective function and subject to certain constraints. Right? This is simple operation research questions. But the interesting point here is the objective function are not only depends on one's own decision, X, but also depends on all the other agents' decision, X minus A, and some system parameters, we call it P, okay? Parameters P and decision XA need to satisfy some global constraint, global equilibrium constraints. And this can be expressed as functional variation inequality. Okay, so for those of you not familiar with this notation, it actually includes some special cases like geometric variation inequality, complementarity constraints, and also the simplest one is the equality constraints. Okay, so the equality, the good news is equality constraints is all we need for today's talk. So let's see how we can adapt this general model framework to our specific problem. Starting with the network, in this case we have a transportation network. And on top of that, there are multiple decision makers. So in this case, we have investor I try to select where they want to invest and how much to invest, right? And we also have multiple individual travelers who starting from a region R and need to go to a destination S. And on their route somewhere, they may need to get charged, okay, to finish their trips. Each of them have their own objective function. So here we're assuming investors just want to maximize profits by choosing location, investment capacity, and supply quantity. And for user J, they have some utility function they want to optimize, right? By choosing the facility location and then travel routes. Okay, this is the general idea. Last but not least, we need to make sure the market is clear for all the locations. So facility supply calculated from all the suppliers' problem, need to equal to facility demand, right? So this is the outline of the remaining of the talk. So in the remaining, I will just formulate this conceptual model framework to the mathematical form, and then develop some algorithm to solve it. Okay, so hopefully this general idea makes sense. And before I proceed, I would like to lay down the key assumptions I made for this talk. So from supply side, I assuming investors are profit maximizers. They compete in a perfectly competitive market, which means they don't have market power to influence the price and influence other people's decision. Okay. And from the demand side, they make two types of decision. Facility choice, we are assuming to depend on three factors. So people will try to find a cheaper location. They will try to avoid some unnecessary travel time. And also they will try to find some places which are more attractive to them. For example, those locations are safer, or maybe they have some coffee shop at the charging station, for example. And in terms of the route choice, we are assuming a very classic notion of traffic equilibrium, or wardrobe user equilibrium. So for those of you not from transportation, the idea is people will always find the shortest route. So in equilibrium, all the routes which are used should have the same travel time, right? Which are less than those routes are used. The last key assumption is both suppliers, both investors and users have perfect information. Okay, so by saying perfect information, we don't mean they know exactly what's the future uncertainty. So they could just know a probability distribution of certain uncertain parameters, right? So starting from the supply side, we use a simple, but I think it's also powerful modeling framework called two-stage stochastic programming. The key idea of this modeling framework is they want to distinguish two types of decision. The first type, we call it first-stage decisions or planning decisions, which we make before we know these uncertain parameters, okay? And the second type, we call it second stage or operational recourse decision. This decision is made after the first stage decision is made and the uncertainties are realized in the future. So people have the flexibility to adjust the system, right? And they may want to optimize second stage cost, subject to some constraints. The idea is the second stage cost will depend on the first stage cost and also the uncertain parameters. And there are multiple criteria to determine what's a good decision, what's the good first stage decision. So here, we just use the basic form. So we want to minimize the first stage cost plus the expectation of the second stage value function. Okay, so the value function is calculated from here. So that's the basic framework. And this is the detailed formulation for supply side in this example. And I would like to highlight the assumption of perfect competition. Because of this assumption, all investors can be aggregated into a dummy investor. So this is a simple conclusion from economics research, right? As long as you use an aggregate investment cost function and operational cost function. Okay, so you can do this aggregation. And second point, there will be no market power to influence travel and charging behaviors. Okay, so it actually makes the problem single level, but multi-stage. Okay. So objective function consists of two parts. The first part is the expected total profits, and the second part is the investment cost. For constraint is simply the capacity constraints for each location for every scenario. Okay, so I don't go into the details, but hopefully the big components make sense to most of you. What's a slightly more interesting part is how we model the demand side, right? To model them individually is hopeless because potentially we have many, many individual travelers. So the strategy we adopt is similar to the user equilibrium using mathematical programming approach. we construct a convex optimization. And the idea is, by solving this convex optimization, we're able to guarantee some properties we desire. Okay, so two properties we desire. The first one is called the wardrobe user equilibrium. This term, if you're familiar with the user equilibrium, the traffic assignment, this is exactly the traffic assignment objective function, right? And then the second property, we hope the distribution of the traffic, of the charging traffic to each location should satisfy some logit choice model, right, with a given utility function. And this utility function consists of three components, as I just mentioned. So this is the locational attractiveness, travel time, and charging prices. Okay, rho here is the prices here. And the constraint is simply the traffic flow conservation. So, but here we need to make sure we consider the immediate stop case. So people may stop along their routes to get charged. So we need to make sure we take it into consideration. And to speak it more formally, why I need to construct the optimization in this way. The main idea is summarized in this lemma. So the optimal solutions of GCDI model are identical with the traffic pattern under the wardrobe user equilibrium and logit for slave location choices. So that's the key idea. And to prove this lemma, the idea is actually very simple. So because this traffic congestion function is monotone increasing, so this term is convex, right? And this term looks complicated, but the key variable is this Q log Q. So this term is also convex in Q. So basically, we can just derive the KKT condition of this optimization, and then we check the notion of wardrobe user equilibrium and logit for slave location choice. Okay. So again, I omit a lot of details, but hopefully I convey the basic idea. The reason we call it generalized combined distribution and assignment model is because we include multiple different special cases. So this is the general cases we consider. The circle is the origin, cross is the destination, and the square is the facility location people want to stop. Right? So people may stop somewhere along their route to get charged. And the first special case is, what if destination is facilities happen at a destination, right? So people just go to a shopping mall to get charged, for example. So this case is actually the classic combined distribution and assignment model, which developed back in 1970s. And the second special case is people make a round trip, an actual trip to get charged. So for example, they don't have enough power the next day, so they need to go to charge and come back home, for example. Right? So we consider all of these special cases. So the last component of the model is the market clearing conditions. So in this case, it's simply the charging supply equal to total charging demand for each location, right? For each location K and for each scenario Xi. The dual variables of these constraints, in economics, the interpretation is prices. So the reason I call it general equilibrium approach is we use the price as a factor to adjust the supply and demand until they balance each other. Okay. And about the definition of system equilibrium is given locational market charging prices rho, there are three conditions need to be held simultaneously. So investors achieve their own optimality, transportation system achieves user equilibrium, and charging market at each location is balanced. Okay, the first two conditions is simply a convex optimization, but because of the third one, the whole problem becomes highly non-convex. And to summarize the computational strategy, I think it's in three keywords. So multi-agent, multi-stage, and multi-dimensional. So we have multi-agent interaction, which lead to an equilibrium problem over network, and it's nonlinear and non-convex, right? And multi-stage, we need to distinguish investment and operation. Multi-dimensional, we have potentially many, many scenarios we need to consider, okay? So next, I will discuss a computational approach that can consider all these three challenges. Okay? So here is the idea. If you look at the objective function more carefully for the investors and travelers, you realize they have a similar structure, which is price times quantity times the supply quantity. And same here, you have the price times the charging demand, right? And these terms, these colorful terms, actually being captured in these market clearing conditions. Right? So if you're familiar with Lagrangian multipliers methods, it's like a reverse version of that method, that approach, right? So the idea is we just need to scale the objective function properly and get rid of these terms, these colorful terms, and add these constraints to our objective function. Okay, so here is the details. We just scale the objective function properly. For example, we need to make some multiplication of some coefficient here and there. And the idea is we put together the investment and traffic assignment into a single optimization problem, right? And we add these constraints. This is market clearing conditions to this big optimization framework. Another constraint I would like to mention is called the non-anticipativity constraints. So the idea is we relax the first stage decision. So C here is the investment of capacity. So we relax it to be scenario dependent, but then add this constraint to make sure they are the same across different scenarios. Okay. And one very important reason and benefits of constructing this optimization is we're able to guarantee the existence and uniqueness of the equilibrium. Okay, it's because the objective function here is strictly convex. Okay, and the constraints are linear. So basically, we're able to find unique solution of this optimization problem, and we're able to prove this optimization, this optimal solution is the equilibrium we want to look for. So basically, we prove there's an existence and uniqueness of our equilibrium. And for the algorithm part, I mainly will relax these two constraints. Okay, after I relax these two constraints, the objective function can be decomposed by scenarios and by agents, right? If you look at this formula, you can solve this part individually and then solve this part individually. Okay, so this is the investment problem and then traffic problem. You can decompose them into smaller pieces. Okay, here's the details. I don't plan to go into that, but the idea is we relax the equilibrium and non-anticipativity constraints and use ADMM approach to decompose the whole problem by scenarios and by agents. Okay, and we call it ADMM stochastic equilibrium algorithm. I'd like to show you some numerical examples. So we test this model using the classic Seuss-Force network. We're using a Seuss-Force network, which has 24 nodes, 76 links. Okay. We select 5 origin, 5 destinations, and 5 candidate facility locations, marked in different colors here. Okay. For link cost, we use the 4th order BPR function, and the base case, we assuming different candidate investment locations are homogeneous, so they have the same attractiveness to each travelers. And here are some coefficients related to travel time and charging prices. For travel demand, we consider 2 scenarios. For deterministic, we are assuming there is 100 trips for each OD pair. Right? And for stochastic case, we randomly sample 20 scenarios out of a normal distribution. So here's the first result I would like to show. Let's focus on these figures first. So the link here is representing the congestion level of each travel link with 0 to 3.4. And the size of the orange ball means how much investment each location attracts. Okay. We can see that although different locations are homogeneous, but because of the transportation network effect, different locations actually attract different investment amount, right? And the trade-off here for users is the price and travel time. So the lower, the higher the charging prices basically means the easier this location can be accessed by travelers. Okay. And next, we consider another case that what if the investor do not consider transportation congestion when they're making the decisions, right? So as we can see, they have slightly different investment decision, and some link may experience a higher congestion level, right? And market start to respond, right? If more people are going to this location, the price may be increased, and then from supply side, people may put more investment because they see an opportunity to make more money. And from demand side, they may choose other route, other location, and choose detour to other cheaper location. And this kind of market dynamics is summarized in the system evolution charts. So this is the convergence of capacities and the convergence of prices from left-hand side to our right-hand side equilibrium. The second result I would like to discuss is the impact of user preferences on equilibrium charging capacity and also travel time. So we consider three cases with increasing price sensitivity. So 0 means people don't care about price when they're making the charging decision. 0.6 means they care more about price and they want to find a cheaper location. This figure shows two types of things. The colorful bars means the investment in each location for different cases, right? And the line chart shows the total travel time for each case. Looking at these bars, with the increasing of price sensitivity, the investment pattern become more and more distributed, right? So people put the investment more equally to different locations. And the reason behind is if people are care about price, they may be willing to choose a cheaper location, which is like a force to driven together the equilibrium price. Right? So in equilibrium, we're expecting similar investment amount. And looking at this line chart, with the increasing of the price sensitivity, the total travel time increase. Right? And this is also nature. If people care about price, they may sacrifice a little bit of travel time. Right? They're willing to detour a little bit. So this is the reason behind. And I think what's more interesting is if you compare these two directly, a more distributed investment does not necessarily reduce your travel time. Right? So if you put the investment to different locations, it actually makes the travel time, the whole network become more congested. Okay. And here are some convergence patterns. So for three cases, we show the convergence of the charging prices, and we show the convergence of the excess supply, so the market equilibrium conditions. So when the excess supply converges to 0, means the system is reached the equilibrium. Okay. And as we can see, the algorithm converges reliably within a few dozen iterations. Here is the solution for stochastic case. Again, the algorithm converges reliably, and here we need to make sure the convergence of two constraints. The first constraint is the excess supply, which is the same as deterministic case. The second convergence is the non-anticipativity constraints, right? So we need to make sure they all converge to 0 to claim the equilibrium is reached. So the last result I would like to discuss is the comparison with the central planar setting, right? A central planar is, we assume it tries to maximize the summation of two components, the traveler's total welfare and total profits of the chargers. And the market-driven setting is what we study here. So each investor, each traveler maximizes its own utility, each investor maximizes its own profits. Okay, so this is where we study here. So this table shows a dramatic difference investment pattern if you compare these two cases. Right? And the reason behind is the externalities that are not able to be captured in the equilibrium setting. Right? People don't care about the congestion they may cause other people, and they don't care about transmission congestion also. And I would like to point out, for this special case, if you think about the resilience, central planar actually put a lot of capacity in just a few locations, right? So if there is a power outage, and it happened to happen in these locations, a lot of capacity will lost, right? So equilibrium seems to give a more resilient investment outcome for this case. And before I conclude today's presentation, I would like to mention, I would like to kind of explain one question you may have. So the algorithm we developed here just work for some special utility function, right? With a specific form, like they consider the charging prices. What if the utility functions are more complicated? Like there is some people not only care about the locational attractiveness, travel time, prices, they also care about the investment, how much capacity in each location, right? So, and also, what if some investors care other objective than the expected profits? So this condition, these scenarios make the algorithm we developed not that applicable. But in 2017, we also have a much more general approach, computational approach developed in this literature. And I just want to quickly summarize the key ideas. So in that algorithm, we formulate the problem as finding the equilibrium prices rho, okay? Such that the excess supply, the charging supply minus total charging demand is equal to 0, right? So the same idea as this one. But we transform this problem into a much more general class of problem, which is finding the maximum points of a bifunction. Okay, so there are some details about how we construct this bifunction. But the idea is, if we solve this bifunction and find the maximum points, the equilibrium price is precisely the maximum points. Okay, but the problem is solving directly this bifunction is still very challenging because it's still non-convex in rho. Therefore, we take the critical third step. We construct a sequence of bifunction to approximate the original bifunction. And the idea is, if this approximation satisfies some properties, which is called lopsided convergence and auxiliary type, we're able to guarantee the convergence of the maximum points of this approximation to the original prices we're interested in. Okay, so the convergence here is guaranteed. It's not heuristic methods. We're able to guarantee the robust convergence. So this slide shows the comparison of the computational time. We implement in the same platform for the general approach and the ADMM equilibrium approach. So as you can see, there's a trade-off, like how general you want to solve the problem and how quickly you want to solve the problem. It's about a magnitude of difference. And I want to mention is, this algorithm do not consider parallel computing. So potentially, because you decompose by scenarios and by agent, you have multiple resources of computing, you can do them simultaneously. So this number could be much lower, depends on how many scenarios you have. And we are not able to solve these examples using path solver or diagonal methods. Okay, so here's the last slide. In this talk, we formulated the development of public charging network in MOPAC framework to capture the interactions between different agents in the system. And next, we show the equilibrium problem can be reformulated as a convex optimization for certain type of utility and objective functions. And ADMM is used to decompose the problem by agent and by scenario. So we can potentially allow for large-scale implementation. And for general case, we also develop a more general computational algorithm based on lopsided convergence. And lastly, talking about future extension. Fundamental idea of this research is we use some market mechanism to balance the supply and demand over a network structure. Right? So if you think about ride-hailing, one of the key questions there is how we determine the dynamic pricing of each location. Right? So we can use the similar framework to kind of estimate what's the dynamic pricing of each location over a network should be in order to achieve the demand-supply balance. And if you think about the system interdependency, think about power and transportation interdependent, there are also some market mechanism involved. For example, how much price you want to incentive people to install the renewable energy, like solar panel or like demand response, right? So this framework may have the potential to apply to that area also. Okay. So hopefully, that's it for my presentation, and hopefully everyone satisfied about that. Thanks.
Let's see if we have any question from the audience.
Thank you for your presentation. I just have a very simple question regarding the utility function you used. How do you define the coefficients of the utility function to be within a reasonable range?
Yeah. So for this talk, I do not specifically explain like how to estimate the coefficient. This is more related to a demand modeling, a large branch of literature on that side. But the idea is you can do the survey to understand how people are sensitive to the price and how people are sensitive to charging travel time, right? So if you want to interpretation, sorry for the. So if you want the interpretation of this coefficient, this one is basically the value of price, right? And this is the value of travel time. The relative scale does not matter too much, because if you fix one, the other one is just relative to that coefficient. For example, if you fix one here, this value is like how much trade-off people willing to pay in order to save 1 minute, for example, right? So that's my answer, but again, I'm not an expert in the demand modeling side.
With your permission from earlier, I would like to make the announcement. If you're interested in this topic, this is a free magazine, Charge Magazine, so you can afford to subscribe to it now. It's published in St. Petersburg by a degreed mechanical engineer, Christian Ruoff. I wish I had told him about your lecture. But it's an easy way to follow trends. If there's nothing of interest, you don't have to read it. This is another interesting new magazine, Autonomous Vehicle Technology. It's free. Right now it is. And I'll leave these out. You can take pictures of them with your cell phones if you like. So if this is the topic you like to follow, some of these articles are technical and some are not. A lot of vendor advertisements. And if you're interested in the construction side of civil engineering, this magazine is free. There's some very expensive magazines in the civil engineering field, but this one is free and it's pretty good. So I recommend those two if you're interested, because the price is right. I'll put them on the table and you can take a picture of the cover if you're interested, or tear out the coupon.
So let's come back to the like commercial.
Yeah, I have nothing to do with any of these magazines.
In a corollary matter, has there been any correlation between the penetration of EV and price of gas?
Obviously, I do not study that problem directly, but I think that this should not be the case, because when I came to US like 60 years ago, the price of gas is really expensive, right? And over the 60 years, the EV adoption is grows kind of significantly, the price is dropping, but it's hard to say it's because of the EV adoption.
So there's no evidence one way or the other?
No evidence yet. And I would say it's more contribute to the slowdown of the development of the third, like China or maybe India. Yeah. But to answer your question, I guess the correlation may be less strong because essentially electric vehicles need electricity, right? And electricity still need energy like power, like thermal turbine to generate. So may not be close related. Yes.
Can you go back to the slide where you compared the central planner and the equilibrium?
Sure.
Oh, you can see. Could you explain again why the central planner is so bad at from 4 to 10? Like it just seems like it's really, I don't know, I'm just a little, it just seems completely different, like a order of magnitude greater, and it comes back down. So why does it make such a big change?
Yeah. So the idea is because they don't care about individuals. They want to maximize the whole system. Right? That's the reason behind. And there are specific settings I don't explain here, like what's the structure. For example, they consider the price of locational price of the charging, because the charging location have some transmission congestion, and also some location have some transportation congestion they hope to avoid. So they just shift the investment to here so that the total system become more efficient. Right?
So, sorry, so what is actually being measured? What is that, what's 34.01? What is that number actually mean? What's the unit?
So the units here may be the megawatt.
The what, sorry?
Megawatt.
Huh, sorry?
Megawatt, so it's the power units.
Oh, okay.
So how many watts we put the charging facility to have. Okay. So this is a capacity measurements. If you consider one people can charge like 10 kilowatts an hour, and the capacity has to be larger than 10 kilowatt. Right? So this is the capacity we're trying to capture.
So, well, sorry. Wait, that's the
Maybe I didn't.
that's the capacity, wait, across,
Capacity of the investment in each location.
and at each node? Is
At
that
each
per
node.
node?
Yeah, so one is, this column is the nodes. So and the map is showing here. So it's not the 5 nodes. Right now we have 11 nodes, right? Because I just tried to replicate a research done by earlier. So I want to use the same setting. And they choose a different number of nodes, which is, I think is 12 nodes, and they do the optimal investment by a single central planner. Yeah.
Okay. Does the total have any significance?
The total is the same because we're assuming an inelastic demand. So the total charging investment need to equal to total charging demand. That's why these two numbers are almost identical.
Wait, so that's a specific node, not the number of nodes?
This is the total, and this is specific node.
Okay. Okay.
Yeah, maybe I can discuss a little bit later.
Okay, yeah.
Sorry about that. Yes?
So can you combine the market equilibrium with the central planner or the system optimum together? Optimum.
So yeah, so for the central planner, the problem is much easier because the equilibrium is directly under their optimization. Right? When they solve a central planner optimization, they need to make sure the demand and supply is balanced. Or they will balance because the dual variables of that is precisely try to guarantee their balance. So they don't have this non-convex property. So this case, theoretically, if it's one stage problem, it's much easier. Okay? And to answer your question, yes, we can consider the market clearing. under the central planner. Good question.
So your problem is just for the deterministic scenario, right?
I show some stochastic. So this is, I guess I just show one result for this case. So I consider 20 scenarios of demand, sample from a normal distribution, and the same algorithm, same modeling framework work. And actually the modeling framework is stochastic. And my understanding is deterministic is just a special case of stochastic. If you just have one scenario, it's deterministic. Yes?
Thank you for that presentation. So you used the ADMM to solve this problem, right? Which is like going to different directions, and what's that performance compared to the L-shaped relaxation, or like sort of Bender decomposition? Because that is also used to solve decomposition. And also another question is how sensitive the convergence rate is to your parameter setting search steps.
Sorry, I don't understand.
The second question is how sensitive is your convergence rate to the parameter settings, like the search steps?
Yeah. So to answer your second question first, it's pretty reliable based on my experience. And the reason is you just have a single or one or two parameters to adjust, and you can adjust them linearly. So if it converges too fast, you just maybe decrease it. If you converge too slow, you increase it. So you're very clear about how you can adjust the parameters. So that second question, I think it's reliably and not very sensitive, right? Although you need to adjust a little bit. And to answer your first question, I don't specifically compare to Bender's or L-shape, but because of the structure, of this model, if you relax the constraint using ADMM, you can decompose to multiple components and using the Lagrange multiplier, augmented Lagrange multiplier methods. So there's a quadratic term that can accelerate your convergence. Okay, so that's the reason we use ADMM instead of,
So does ADMM guarantee to converge in the end, or because it seems like a Lagrange relaxation type of thing?
No, it's guaranteed. So the convergence is guaranteed. That's the beauty of ADMM. It's simple, but it can decompose the large problem, and the convergence is guaranteed. But one caveat is
the problem is not integer.
it's not integer.
It's convex.
It's convex.
Yeah, of course.
So you can introduce the integer, but I guess ADMM is not ready for integer.
Yeah, I think you can still solve integer, but the gap is not going to be zero because this is a convex problem. So if you use like
I agree.
decomposition, you can always get 0% gap theoretically. But if there is integer constraint,
It's much challenging, yes.
It's not going to converge.
Yeah. And one.
You have some location problems, but why don't you? Is there any planning like location problems? Why the problems? I missed that first part.
Yeah. So actually, this is like it's actually a foundation of my current research. So the next step is I want to control, and I want to do the central planner control to influence this market interaction. So that's the whole idea. We need to understand the market interaction first before we control the system. Yeah.
No further question. Okay. Thank you, Dr. Guo. Thank you very much for your excellent presentation. Next, we don't have a specific talk speaker. Next week at the second time, we're going to have the IT data